Okay, so first of all, I would like to thank the organizers for inviting me here and giving me the opportunity to present my work. So this is a talk about rigidity phenomena, and in particular two manifestations of it which have come up in recent work, and they concern forbidden regions and maximal degeneracy. So I will go one by one and try to unravel all this terminology for you. So to begin with, we will begin from the basic and start with the Poisson point process, which is the most popular model of random point sets and in Euclidean space, for example. It is characterized by spatial independence. So if you take two disjoint spatial domains, then the points in these two disjoint spatial domains are statistically independent. And that's partly the main driver of the popularity of the Poisson point process, because you can pretty much calculate anything you want. But some of the most scientifically interesting models of random point sets are strongly correlated. So, in fact, many of them exhibit mutual repulsion. So these include the GUE eigenvalues, zeros of random polynomials, etc., about which some of you know more than I do. So in this talk, we are mostly going to focus on the question of spatial conditioning. So if the model is strongly correlated, then the spatial independence of the Poisson point process is lost, and the question of spatial conditioning becomes a non-trivial one. And to put things on a concrete footing, we will spell out the main question as follows. So suppose we are given a domain D, and suppose we are aware of the point configuration outside D, then we want to infer something about the distribution of the points inside D. And generally, you would anticipate that there will be some, if the point process is comes from a reasonably nice distribution, for example, GUE eigenvalues or the zeros of Gaussian random polynomials, you might expect that this kind of conditional distributions, although they lack the simplicity of the Poissonian structure, but still they should exhibit some amount of regularity. However, it turns out that this kind of spatial conditioning leads to remarkable singularities in the distribution of the points inside the domain, given the point configuration outside. And roughly speaking, this is what we refer to as rigidity. So the most basic instance of rigidity is what we call the rigidity of particle numbers. And at this point, I would like to mention that there are several notions of rigidity which are in vogue concerning this kind of random matrix type processes. And broadly, at a very broad level, they are, they are related in some way, or they are, in some sense, you can say that they are manifestations of similar underlying reasons. But rigorous theorems, for example, Shishendu will talk about some kind of rigidity in his lecture tomorrow. But rigorous theorems exhibiting equivalence between these concepts is few and far between. So the most basic instance of rigidity is the rigidity of particle numbers. So it basically means, in simple language, that the number of particles in a domain is a deterministic function of the particle configuration outside the domain. So a key element of the rigidity that we are going to talk about in today's presentation is that our results are almost sure. So the number of particles in a domain is not only strongly influenced probabilistically by the configuration outside the domain, but it is completely determined by the particle configuration outside it. So this amounts to a local law of conservation of mass. So we are not allowed to perturb the point configuration in ways that create new particles or delete existing ones. Because if you take an interval in the random matrix process, for example, and you freeze the point configuration outside, then rigidity of particle numbers tells you that the number of particles inside is conserved. So you are not allowed to change you are not allowed to perturb the point configuration in a way which changes the number of particles. And this has implications in the study of stochastic geometry on these point processes, but notably in the use of Barton and King type arguments, but we will not have the occasion to get into that today. So rigidity of particle numbers has been shown to occur for the Dyson log gas, which is the sign kernel process coming from the GUE eigenvalues, and the 2D Coulomb gas at inverse temperature beta equal to 2, so the Ginevra point process. And it has also been established for the zeros of the planar Gaussian analytic function, about which is also a popular topic here. And in subsequent works, rigidity of particle numbers was established for a variety of determinantal processes in the works of Bufetov, Chiu, Osada, Shirai. And I'm not reading out the names of the various processes for which they have established rigidity of particle numbers. But I would just like to mention in the passing that all these processes, determinantal processes for which rigidity is known to occur, correspond to projection kernel determinantal processes. And in joint work with Manju, we showed that projection kernel is actually necessary, so you cannot do without it. And at this point, I would also like to just to give you an overview of the works that are going on in this field. I would like to mention some very recent works by the French groups of Reda and Najnoudel, and also the group from Lille involving Dereudre, Hardy, and Meda, along with Thomas Leblé, who have also worked on rigidity in the context of Coulomb gases. So let me just sort of lay out the picture in a more technical manner, and then I will move on to sort of the main results that I want to discuss. So in general, for a point process and a bounded domain, if the point process is pi, we will call pi in the point configuration inside the domain, and pi out the point configuration outside the domain. So, and we will consider various observables of the point configuration inside the domain. So and we are interested in some observable, which is defined on the basis of the points inside this domain of pi out. So just to extend the notion that we talked about while discussing rigidity of particle numbers. And an important class of such examples of observables which we would consider are linear statistics. So you take your favorite test function phi, apply it to each of the points inside your domain, and sum them up. So this is the linear statistic of the inside points corresponding to the functional phi, and this gives you, this is an important class of observables. And just to give an example, notice that a simple example of this is when you can set phi to be the indicator of your domain, and then the corresponding linear statistic just turns out to be the number of particles in D. But it's natural to ask about the rigidity of more general functionals other than the particle count. So for example, you could take phi to be, so if your point configuration is on the plane, on the complex plane, then you can take phi to be the complex powers of lambda, and then you can talk about the rigidity of higher moments of the points in D, okay? So, and with Manju, we showed that if you consider the following generalized family of planar Gaussian analytic functions. So in the standard case, you have this parameter alpha to be 1, but you can consider it for general positive alpha, and the zeros of this family of Gaussian analytic functions exhibit conservation or rigidity of moments of various orders depending on how you choose your alpha. And we have a precise description of that, okay? So the general picture is that the rigidity of particle numbers is connected with suppressed fluctuation of suppress fluctuation of the particle numbers. So for example, it's a well-known fact that if you take one-dimensional random matrix type ensembles, then the fluctuation of particle numbers grows like the logarithm of the interval. If you take it in 2 dimension, it grows like the size of the perimeter of the domain. So in other words, we need the fluctuation of particle numbers to be smaller order of the volume of the domain. And rigidity of general observables is connected, and rigidity of particle numbers is related with the suppressed fluctuation of particle numbers. And rigidity of general observables is connected with suppressed fluctuation of other linear statistics. So it's also connected with faster decay of whole probabilities and singularity of palm measures. So as I already mentioned towards the beginning of the talk, that there are these various notions of rigidity or suppressed fluctuations which are in vogue, and I have listed out a few of them, but there are very few theorems which actually, rigorous theorems which actually connect these ideas. So let me just mention one. So basically it says, so I will not explain this in great detail because this is just to give you an idea of the background. So this basically says that if you have a point process with on the plane, let's say, with the first m moments of the process rigid, so the particle number, the mean, and up to the first m moments are rigid, then if you consider the palm measures corresponding to tuples of points for this process, then the mutual absolute continuity and the singularity of these various palm measures can be shown to be equivalent to the level of rigidity of this process. But there are very few rigorous theorems establishing general implications like the above between these concepts. Well, I mean, we will consider it generally, and depending, so for example, if it is Poisson, then K can be different from L, right? So it depends on the level of rigidity. As soon as there is some rigidity of particle numbers, you have to take K equal to L, otherwise there is no chance of continuity. Okay, so let me come to the two main results that I am going to talk about in today's talk. So here we are going to focus on the phenomenon of conditioning on a large hole. So what is a hole? So suppose we are considering planar point processes. So we say that a disk is a hole if there are no particles inside the disk. So it's a particle-free region. And just to mention at this point, so there is no need for this to be a disk. It could be of a more general shape, but more general shapes are harder to study and prove theorems about. So disk is somehow the first go-to point. So we say that a disk is a hole if it is particle-free. And we look at the conditional distributions of the points outside D, given that D is a hole. So in some sense, it is the reverse conditioning of what we have done here. So here we are conditioning that there are no particles inside D, and we want to study the outside particle configuration. And just to give you sort of a preview of where we are heading to, so generally, if you take your domain, if you take your disk to be very big, the fact that there is a hole in that big disk is a rare event, and essentially you want to understand what is the special outside configuration which causes such a big hole to appear. So that's the moral of the story. And when you make the radius of the disk very large, how does the outside configuration behave? So what causes a large hole, which is a rare event to occur, is our focus of investigation. And this question was investigated first by Jankovici, Leibovitz, and Magnificat for 2D Coulomb gas at beta equal to 2, so for the Ginevra ensemble. And what they showed is this picture. And so their paper is of more of a physical nature, but essentially they contain the main ingredients for a rigorous investigation. So this is the hole. This has been scaled down to have unit radius. So the entire particle system has been scaled by the radius of the hole. So it turns out that is the scale at which interesting phenomena can be observed. So this is the hole. And outside the hole, away from the hole, there is the distribution of the particles is like the equilibrium distribution. So in expectation, this is like the Lebesgue measure. However, the interesting feature is that at the edge of the hole, there is an accumulation of particles. So if you take this scaling and let the radius of the hole go to infinity, in other words, take the scaling parameter to infinity, then basically the outside would converge to the Lebesgue measure and the edge of the hole would converge to a singular distribution on the edge of the hole. And the specific masses of this singular measure at the edge of the hole are also known. And at this point, I would also like to mention that Adhikari and Reddy, one of whom is in the audience today, have also investigated this using potential theoretic methods, but they are more focused on the calculation of hole probabilities for holes which are of a more general shape than a disk. So this is the situation in how things stand in 2 dimensions. In 1 dimension, which is perhaps even simpler, but the paper came out later. So this was, in 1 dimension, it was investigated by Manjunath, Nadal, Scardiccio, and Vivo for the Dyson log gas. And what they showed was the following. So here, so this is the hole, again scaled to have unit length. And what happens is that the zeros outside, or the particles outside, they do pile up at the edge of the hole. But a crucial difference between the 2-dimensional picture is that in the 2-dimensional picture, you get an actual atom, an actual singularity at the edge of the hole. So here, you get a singularity in the form of blow up of the density, but you do not get a delta measure, so you do not get an atom at the edge. So this is the situation that is known, and let me sort of heuristically justify why it should be natural to expect a picture like this. So remember that suppose we are given a typical configuration from the Geneva ensemble, and we are given the duty to create this huge hole. So how would we go about it? So generally speaking, we would, if you take a typical configuration and try to take a point and move it far away from its typical location, it would cost you energy. And in terms of physical heuristics, you would like to create this hole by expending the minimum amount of energy that you need. So we want to do the least amount of work that we absolutely need to do and yet create this hole. And we know that if we are not allowed to delete points because of particle number rigidity, and we also know that if we move points far away from their typical location, then we pay in terms of energy. So the solution of this conundrum is to take the particles inside and move them the minimum distance possible, which is to the edge of the hole. So heuristic, in terms of physical heuristics, this justifies as to why a picture like this, or for that matter, a picture like this, is plausible. So any questions so far? Okay. So this is how things stood, and in the context of this, let me present the first theorem that we are going to discuss today. So we consider this problem of the conditional distribution given a large hole, for the zeros of the standard planar Gaussian analytic function. And in joint work with Alon Nishri, we show that the conditional distribution given a large hole looks like this. So let me walk you through this picture. So what is there? So this is the hole. So this is the hole, again scaled to unit radius, because as we already discussed in these sort of problems, scaling the hole to unit radius is the interesting scale at which you can observe phenomena. So this is the hole, and this is the distribution of the points far away. So definitely they look like the distribution of the Coulomb points far away. So that is only expected. You also have a singular component at the edge of the hole. So this is also on similar lines to the GUE or the Ginevra case. However, the interesting feature for the zeros of the Gaussian analytic function is that in between the singular component at the edge of the hole and the equilibrium component far away, you obtain a region which we call the forbidden region, which is almost devoid of zeros. And in particular, the density of zeros vanishes as r goes to infinity here. So if you did take the limit and describe this picture in terms of the limiting measures, the limiting measure would put zero mass here. So this is something which is not easily explicable by the physical heuristics that we discussed. So let me state this result in terms of a more formal theorem. So the conditional intensity of the zeros of the Gaussian random polynomials have the following behavior. So there is a singular component at the edge of the hole, which is this one. There is a subsequent forbidden region in the annulus, and the outer radius of this annulus is square root e. So in this region, there is a forbidden region where the conditional intensity goes to 0 as r goes to infinity. And beyond square root e times r, the conditional density behaves in the limit like the equilibrium density. So, okay. So I see that I have half an hour left. So this is a relative comparison of the Ginevra case and the zeros of the Gaussian analytic function. And there is we can discuss something about the ideas of the proof, but maybe for the moment we will skip it and try to come back to it later when we have time. So we now move to the other main result that I intended to talk about, which is about what we call stealthy random fields. So the nomenclature is borrowed from the physical literature. So stealthy particle systems and more generally stealthy random fields have gained some attention recently in condensed matter physics. So Torquato is one of the leading people working on it from the physical side, but also Stillinger, Batten, Zhang, Chetkov, Carr, Distasio, and a lot of other experimental physicists. So basically what we are doing is the following. So suppose I have a random field, and let's say indexed by ZD or by RD. So suppose I have Xi, where I is in ZD, or U, where U is in RD. Like this. So if the Xi's are 0 or 1, we are discussing particle systems. But Xi's, there can be many other interesting variants. So for example, the Xi's could be continuous random variables, so it can be Gaussian random variables, a Gaussian field. And actually, almost all of the results that we are going to discuss today on this topic actually even go through for random measures, if the XUs are actually DXUs, which is a random measure on RT, even that is okay. But basically, the situation we are looking at is as follows. So this is a translation invariant random field. So, so the correlation function, which is covariance of xu comma xv, is just a function of k times u minus v. So it's just a function of one variable because of the translation invariance. And what we are interested in is S, which is the Fourier transform of k. So in the physical literature, this is a very popular and important object. It is called the structure function. And actually, if your xi's are atomic random variables, so for example, a particle system, you have to adjust this Fourier transform by subtracting of delta mass at 0, but but basically this is what it is. So this is the structure function. So this is going to be an important object, and essentially this is the spectral measure. So if the spectral measure has a density, then S is just the spectral density. But again, in the more general setting, this Fourier transform could just be a measure. So a random field is stealthy if the spectrum of the process, that is S, has a gap, namely it vanishes in the neighborhood of the origin. In other words, there is a neighborhood U containing the origin such that S is identically 0 on U. Okay? And there can be some variants where this neighborhood might or might not contain the origin, but for simplicity, let us stick to the standard or the initial way this was introduced. Okay? So this is what we are looking at. And just for a moment to explain the nomenclature stealthy, the nomenclature stealthy was introduced because in the applied literature, if you study such systems using diffraction experiments, then these systems are invisible to diffraction experiments if you hit it with waves having frequencies in this gap U. So that's the sort of where the name comes from. And before going to some of the main results, I would also like to mention that recently, so one particular model of one particular case of this is when when you consider Gaussian random fields having this constraint of spectral gap. And that kind of system has been studied, has gained some attention recently. So here Manju and Krishna have worked on it, and also in Israel, Feldheim, Nazarov, and Nitzan, they have worked on the whole probabilities for such processes. So here what we are going to focus on is some conjectures about this kind of systems coming from the physical literature. So Stillinger, Zhang, and Torquato conjectured that stealthy particle systems have deterministically bounded holes. So deterministically bounded holes means that there is a fixed number 10 such that if you take any realization of the process, then any hole cannot be bigger than radius 10, and with probability 1. And this conjecture they arrived at by experimental considerations, by simulations. And it always struck me as remarkable as to how by experiments you can distinguish between something which is bounded with probability 1 and something which is growing like log n, but apparently they were convinced that the holes were deterministically bounded, and the point is that they were right. So in joint work with Leibowitz, we showed that stealthy random fields, so I'm coming to the conjecture of bounded holes in a moment. But the first result that we showed about stealthy random fields, and here we do not need particle systems, we showed that stealthy random fields exhibit maximal rigidity. Namely, if you have any random field, and including a Gaussian random field having this property, having this spectral gap, then if you take a domain, and if you know the field outside the domain, then you can exactly calculate the field inside the domain. So this is, and this holds very generally as soon as the spectral gap condition is obeyed. So even for random measures obeying this property. And the same conclusion holds if instead of a gap, the spectral density S decays fast enough at the origin. So you can relax the condition of spectral gap a little bit. And of course, an interesting special case is a Gaussian process with a spectral gap, because Gaussian processes are interesting, and particularly those with spectral gap have also gained some traction in the recent years. So this is the first result that I would like to mention about random processes with spectral gaps. The next one is going back to this conjecture of bounded holes. So holes in stealthy particle systems are bounded deterministically with a universal upper bound, and we can also show that this universal upper bound for the holes of the system can be taken to be inversely proportional to the size of the spectral gap. So in some sense that is natural, because the smaller you are making the size of the spectral gap, the more you are proceeding towards the situation with no gap, and so the effects of the gap are becoming lesser and lesser, in that the bound on your hole size is going bigger, growing bigger and bigger. So you are allowed to have bigger and bigger holes. Any questions about this? And actually, you really do not need a particle system. Any random field having which takes values in a finite alphabet is fine, and probably you can do with even a one-sided bound on the values of the random field. But this is the natural setting in which the conjecture was posed. And we also, so bounded holes basically tells you that particles cannot be too far apart. Yes? I'm sorry? Okay, so there are two ways you can make this continuous. So you can make the indexing variable continuous, and you can make the alphabet continuous. If the alphabet is continuous, maybe you can get by if you have, for example, a lower bound on the values taken by the alphabet, but we did not find strong enough motivation to push in that direction. I'm sorry? For that it is not true. No. Nazarov, Feldheim, Nizan, and Buckley. So their result shows that the whole probability decays like a Gaussian. Upper and lower bounds, so in particular lower bound. Yeah. Okay, so bounded holes basically is telling you that points are not allowed to be too far apart. Points prefer not to be too far apart, okay? The next part tells you that they are not allowed to be too close together either. So the particle number in a domain, of course, in any domain you have an expected number of particles. Let's call it expectation of n. And in general, we are used to results where n is the actual number of particles is expectation of n plus some fluctuation, which is usually Gaussian or something like that. So here, what we can show is that the number of particles in a domain is bounded with probability 1 by a constant multiple of expectation of n. So that shows that the number of particles on one hand cannot be too far apart, the particles cannot be too far apart on one hand, on the other hand they are not allowed to be too close together and cluster either. And in some sense this tallies with the idea of maximal rigidity, because somehow maximal rigidity is saying that the process is very, it has very low randomness in some sense. And bounded holes and anti-concentration together is somehow corroborating to that idea. So before I go on to some discussion of the proof ideas, let me also mention that I made this comment short while ago that maximal rigidity somehow morally it indicates that the system has low randomness. So one way to measure the randomness in a system is to consider the entropy. So in particular for a stochastic process, you would be interested in the entropy of the variables falling in a certain domain and divided by the size of the domain, so the entropy per site, and your usually physically interesting object is when you take the domain size to infinity. Entropy per site as the domain size goes to infinity. And so of course we would be interested in measuring this for this kind of stealthy processes and try to interpret the degeneracy in terms of the entropy per site. And there we have some very recent progress, but I did not formally include them in the slides because the paper is still being written. So basically and there we have a continuous and a discrete version. So we will be dealing with the case when the index set is discrete, because otherwise the entropy will be problematic in the continuum index set. But the excis, so case one is that when the variables are continuous, the excis are continuous random variables with densities. In that case, we can show that this is minus infinity for any such process. And so this is continuous. So here we are discussing the differential entropy per site. And if the xi's take values in a finite alphabet, let's say between 1 and n, where n is fixed, this limit is 0. This is discrete. And the interesting part is the following, that it is also, in principle, one might be tempted to relate the question of entropy to the maximal rigidity, particularly in the case of the one-dimensional situation. So if you have Z, and if you have a random field indexed by Z, and your field and your random field is xi, then maximal rigidity would mean that if you take a big interval, then the xi's outside this interval completely determine the xi's inside this interval. So you can take, so in other words, the sigma field generated by the xi's outside is full. And now you can let this interval go to infinity, and this tells you that the two-sided tail sigma field is full. Now in one dimension, and specifically in one dimension, there is a theorem of Rochlin and Sinai which tells you that if the one-sided tail sigma field is full, then the entropy per site has to be degenerate. However, here we have two-sided tail sigma field, and it might seem to be very tempting to do some hocus pocus and try to reach the one-sided full tail sigma field from the two-sided case, but apparently it's not doable, and apparently these two things are not even equivalent. So we have different methods for doing this, and some of it is absolutely, particularly in the discrete case, involves figuring out the configurations by hand and counting them by hand, but this is work in progress. So I have a few more minutes, so let me go back to some of the main ideas of the proof. So first let me discuss a little bit about the forbidden region. So just to remind you of the result, we are interested in the conditional behavior of the outside points or the outside particles, the typical configuration of particles outside a big hole, which can create this rare phenomenon of having such a big hole. And what we are showing, so this is the picture for the Geneva ensemble, which is the Coulomb gas case, and this is the picture for the Gaussian zero ensemble. And what we can show is, what we are showing is that at the edge of the hole there is a singular measure, far away there is an equilibrium measure, but in between there is a surprising forbidden region. And what we do is the following. So our main ideas are based on large deviations for zeros of random polynomials. So we are discussing zeros of Gaussian analytic functions here. So the analytic function has a power series expansion, and we take polynomial truncations of that and let the degree of the truncation go to infinity. And that's how we approach the analytic function via the polynomials. Of course, what we are interested in is the zeros. So polynomials are going to analytic function, but what we are really interested is the zeros of the analytic function. So we have to study the zeros of the polynomial and have some control on how the zeros of the polynomial, how close the zeros of the polynomial are to those of the analytic function, and obtain some quantitative estimates of that. So that part can be tricky in some situations. But nonetheless, at a broad level, we will be using large deviations for zeros of polynomial truncations of the Gaussian analytic function, and the main ideas are inspired by a paper of Ofer with Steve Zeldich. So if you think of a polynomial, random polynomial, so let's say a polynomial truncation of the Gaussian analytic function, and if you consider Z to be the zeros, so instead of zeros, if you have a set of zeros of the polynomial, we would always pass to the corresponding empirical measure. That's somehow the natural or the canonical way of looking at things in this setting. So Z is the zeros, it's the empirical measure of a particular configuration of zeros. Then the probability of having this configuration of zeros is basically via these large deviation arguments is basically given by e to the minus r to the 4 times I of Z, where I is the large deviation principal rate function. And I will be soon coming to what I is explicitly. So what is R? So basically the situation is as follows. So we want to study the whole of radius R, okay? To study the whole of radius R, we determine in terms of R, what is the right truncation of the Gaussian analytic function. We have to truncate the Gaussian analytic function at a sufficiently high degree, depending on R, such that the zeros of the polynomial at that truncated degree gives a good idea of the zeros of the Gaussian analytic function when you have a whole of radius R, okay? So the truncation degree depends on R, and the large deviation is on these truncated polynomials, so of course they depend on R. R is the parameter that is going to infinity. The large deviation is of this form. So I is the LDP rate function, and I will be coming to the explicit description of that in a moment. So no zeros in the whole D is the same as the empirical measure of the zeros putting no mass on D. So that's the natural interpretation. And to find the most likely configuration, given that there is a hole, is basically saying that I am looking at configurations or empirical measures Z such that Z of D is 0. So the probability of having any such configuration is e to the minus r to the 4 times I of Z. So so the maximum among this kind of among these configurations which satisfy the whole condition is obtained by minimizing I over empirical measure Z such that Z of D is 0. So that's the sort of the natural correspondence. That's what we, morally that's what we do. So this constraint so this is a constraint optimization problem. It's optimization because you are minimizing the large deviation rate functional. It's constraint because you constrain by the whole condition that that your measure puts 0 mass on the whole. And it's a optimization problem on the space of probability measures. So it's on the plane. So it's an infinite dimensional problem. And the functional I, which is the LDP rate function to be optimized, is highly non-smooth. So it is of this form. So U is the logarithmic potential of a measure mu. I of mu is the potential minus this Gaussian subtraction. And then you take supremum over Z. So this is kind of a highly non-smooth term. And sigma is the logarithmic energy. So U mu W and sigma of mu is log W d mu Z d mu W. So just to have a case in comparison, so the case of so a similar approach can be taken for the Coulomb gas of the Geneva ensemble, and there the rate functional is something, and up to constants it's something like the integral minus. So I am probably making some mistakes in the sign and the constants, but basically it is like this. So the key point is that this is, if you think in terms of mu, this is a nice quadratic expression in terms of mu. So that's kind of easier to handle. Here you have this non-smoothness in the space of infinite dimensional measures, so that's a little more complicated. And the problem is that, and because as an upshot of for example, this non-smoothness, there is no clear variational method available. So we tried a lot to obtain this via honest variational method, but it's not clear how to do it. And in part because the ground truth, which is your true minimizer, has this kind of a singular component, and those are not easy to capture by variational techniques. I have 5 minutes. Okay. So basically we bypass this optimization problem by doing the following. We guess the solution, and how do we guess the solution? So there are well-known results about the whole probabilities. So what is the asymptotic probability of having such a big hole? So many people have worked on it. Manju has worked on it, and there are works by Yalon Nishri on it. So basically, in these large deviation problems, in these large deviation theorems, they have upper and lower bounds for the whole probabilities. And in particular, the lower bound for the whole probability gives you an event. It creates an event in terms of the polynomial which gives this large hole. So what we do is that we just focus on this particular conditioning on the coefficients of the polynomial, which is much easier to deal with, that gives you the large deviation lower bound. And basically look at the distribution of the zeros given that conditioning on the coefficients of the polynomial, okay? And that tells that, and then you can do some simulations and guess the solution. And once you can guess the solution, you can use potential theoretic methods, again, partly inspired by work of Offer and Zeldich, that and establish rigorously that indeed this highly singular measure is the minimizer of the constraint optimization problem. So, and the heuristics are made rigorous by obtaining effective versions of the large deviation estimates and approximating the analytic function zeros by those of the polynomial. So some quantitative control here. So this is about the heuristics for the forbidden region theorem. So let me give you a quick overview of what we can do for the spectral gap processes. So if you have a random process with a spectral gap, so the spectrum is vanishing or decaying very fast in a neighborhood of the origin, let's say. So the existence of this spectral gap can be exploited to construct linear functionals of the process which have low variance. And a linear functional with a low variance, you can think of it as approximately constant. So this gives you an approximate linear constraint on your process. Because a linear functional of your process will be just summation phi I xi. You just consider process on Z, for example. So if this is approximately constant, that means that you have a linear equation, linear constraint on the process. And if you can obtain a sufficiently rich class of such constraints, you can take the closure of such functionals and deduce degenerate behavior. So for example, you can pass from this kind of functionals to the characteristic function of the measure restricted to the domain. So this is all that I had in mind. So thank you for your patience.